Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Chris Smith.
I have good news for people that like to keep their mind active, because a piece of research that's being announced later this year by Jonas Gedde, who's a neuropsychiatrist at the Mayo Clinic in America, suggests that it's definitely a case of use it or lose it. He recruited 1,300 people who were aged 70 to 89, and 200 of them had mild memory defects and were beginning to struggle to remember things they'd just done. But 1,200 of them were fine. And what they did was to quiz these people on their lifestyle, what they like to do for social activities, what they like to do to keep themselves busy. And they asked them about this from various aspects of their life, not just the present day. Mm-hmm. And what they then did was to compare their performance at memory tasks with what they reported their habits were. And a really strong pattern emerged. People that kept themselves sort of cognitively most active did best. They had the best cognitive activity, the best mental abilities, and they were less likely to have memory deficits. And the things that worked really well in their favour were things as mundane as doing the crossword, having a conversation with other people, socialising, doing pottery, knitting. Bad for you things, though, were watching television. People who watched more than 7 hours television a day were twice as likely as people who watched less than 7 hours television a day to get memory problems. So I think there's a lesson in there for everyone, isn't there? What impact television could have on you, especially the kind of television that we've got on at the moment. But yes, the slight query over this kind of research, though, is it cause or effect? In other words, do people who are more active, they're more likely to socialise with people, they're more likely to read things? Are they just intellectually better able to start with, and therefore they've got more to lose, and therefore as they get older, they end up better off? Well, what they want to do to try and solve that one is because, as Gedde himself says, they know a lot about this study population now. They've got all these people, they're following them up, and they're now going to do what's called a prospective trial. They're going to follow them over a period of time and see if the people who are currently the most active go on to remain the best performers cognitively for the foreseeable future. So I guess we'll just have to wait and see what the long-term outcome is. But certainly the short-term lesson in this is use it or lose it.
I think so. I mean, my mum always keeps her brain active, and she's fantastic. She's incredibly positive. Right, well, let's start off with the questions for Dr. Chris. Dr. Chris, Andrew in Cambridge asked, when an electric kettle is switched on with cold water in it, it makes a very loud sound, but just prior to boiling, the sound almost goes away. Why is that?
Well, I think the answer to this is a phenomenon called cavitation. And what this is the collapsing of tiny bubbles under the conditions of cold temperature. So if you have a kettle full of cold water, the element superheats the water around the element to a very high temperature, and this causes the water to expand and form bubbles, vapour if you like, little steam bubbles, just in the vicinity of the element. Of course, those steam bubbles are much less dense than the rest of the water in the kettle, so they'll try and rise towards the surface in exactly the same way as if I blew up a balloon underwater or I blew out some air bubbles underwater, they'd try and rise. Of course, as the bubbles rise, they come into contact with much colder water further up the kettle, and this takes the heat away from the steam bubble, which makes the bubble then collapse on itself, and as it collapses, it goes bang. And I think those sort of rumbling noises you get when the kettle is just warming up to start with are because those bubbles are cavitating, collapsing in on themselves. So why does the sound go away as the kettle gets just towards the boiling point? Well, once you get towards boiling, almost the entire kettle is full of water at uniform temperature. So as the bubbles get towards the surface, instead of collapsing in on themselves, they make it from the bottom of the kettle right out of the top, and they emerge as a bubble with steam, and you see the steam coming off the kettle, and so that's why the sound goes away as the kettle nears boiling point.
One of those joyous moments, isn't it, when the kettle's boiled? Thank you very much, Dr. Chris. Let's go to an email from Leanne. She says, science question, why is oxygen called O2? Chris?
Well, the reason, Leanne, is because oxygen, O, that's the chemical symbol for oxygen, actually hangs around in pairs. It gets lonely on its own, and it teams up with another oxygen atom to form an oxygen molecule. There's two of them, so we call it H2O2, because in chemical formulae, you use the number after the letter to tell you how many of each of those elements there are. So H2O is 2 hydrogen atoms stuck to 1 O, oxygen. And the reason oxygen does that is because it's in group 6 of the periodic table. And that means that in its outer shell, it has 6 electrons. And most atoms want to have 8 electrons in their outer shell. That's just the way it works. If you look at a noble gas like helium, for example, no, helium's a bad example. If you look at a noble gas like argon, for example, they all have a full shell of electrons around the outside of their atoms. And that means that you've got 8, and that's the most stable electron arrangement or configuration. Now, if you're an atom of oxygen and you've only got 6 electrons, you haven't got that magic 8. You're not very happy. So the way around that problem is to go and find another atom of oxygen, and if the two of you get together, you can share some of your electrons together. And in this way, because you're sharing electrons, you can make each other think you've got the full complement of 8, and that's called covalent bonding. And that's why some things like hydrogen does it, oxygen does it, lots of things will link together and share their electrons in these covalent bonds to make themselves have those magic numbers of electrons that is the stable configuration.
Fantastic. Thank you, Dr. Chris. Now then, let's go to the phones this time. We've got Tony in Chelmsford. Hello, Tony.
Hi, how are you?
Yeah, very good. And your question?
I've got 2 very quick questions, both about the Earth. Where if you were to put something on a ball and spin it, centrifugal force would throw that thing off the surface of the ball. So if the Earth is spinning at thousands of miles an hour, why do we not all get thrown off of it? And then
Hi,
secondly...
Tony. But the Earth is actually doing about 1,000 miles an hour at the equator, because the Earth is about 24,000 miles around its middle, and there's 24 hours in the day, and that therefore it must be going at about 1,000 miles an hour, because you said thousands, but the surface of the Earth at the equator is about 1,000 miles an hour. If you were to stand at the North Pole, effectively you're not doing anything, you're not moving, which is quite funky, blows your brain a bit thinking that, doesn't it? But you're saying, why don't the people standing on the equator get flung off into space?
Yeah.
And the simple answer is because of gravity. The Earth is massive. It's about 10 to the 24 kilograms is the weight of the Earth. So in other words, 20, that's 24 zeros after a number 6 is about the weight of the Earth in kilos. And because it's so massive, it's got a huge amount of gravity. And that means that even though your personal gravity isn't very high, then the Earth is still hanging on to you very tightly. It's pulling you down. And to leave the Earth's surface, you have to be going about it's more than that. It's about 20,000 miles an hour. You have to get up to that sort of speed to escape from the Earth's surface. So even with the best will in the world, the fling you get at 1,000 miles an hour is insufficient to make you depart from the surface of the Earth. And good job too.
Okay. My other quick question is, in my understanding, perpetual motion is impossible. So how does the Earth keep spinning? Is that not perpetual motion?
Yeah, I mean, that you're right. Perpetual motion can't exist because the sense of perpetual motion is something which has energy which comes from nowhere. But the Earth has energy because it's very massive and it's made by gluing lots of tiny particles together. When the solar system formed, that was about 4.5 billion years ago, a giant ball of dust and gas was hovering in space, and we think that a big star nearby buffeted that gas so that it began to collapse in on itself. And as it collapsed in on itself, it first of all formed a proto-star, and that proto-star then was spinning, and the material around it was spinning, and as the material around it slowly formed into small planetesimals, little bits of planets, because all the material is turning and spinning, it can't lose that spin. There's nowhere for the energy to go. It has to add together. You can't get rid of your momentum, and it's called conservation of angular momentum. And so all the bodies that got formed in the solar system, all the planets, all had this spin preserved in them. So the Earth is turning, and because the Earth is turning in space, there's virtually no way it can lose that energy. It can't give the energy to anything, and so therefore it's going to keep spinning for a very long time. But that's not the whole story, because when the Earth was first born, about 4.5 billion years ago, it ended up on a very similar planetary trajectory to another planet, which is notionally called Theia. Theia doesn't exist anymore. It was about the size of Mars, and because Earth and this other planet ended up on the same trajectory, they bashed into each other. And Theia got largely absorbed into the Earth, but in the ensuing collision, some of the Earth's crust material got thrown up into space, and it made the Moon. And this crust material coalesced to form the Moon as it is today. The Moon orbits the Earth, And as you all know, the moon causes tides. We have high tides and low tides because of the fact that the moon is sitting outside the Earth, or sit around the Earth, and pulling on the Earth's surface, and this attracts water. And as a result, because we're moving lots of water around on Earth, that water is actually using some of Earth's energy, because the Earth is losing some of its energy in the form of tides. And the way it's losing it is that the Earth is turning slightly faster than the moon is going round it, of course. And as a result, because the Earth is turning 24 hours in a day, the moon takes a month to go around the Earth. So the Earth is always dragging on the moon a little bit. And as a result, the moon is stealing some of our spin. This is making the moon speed up in space. It's a bit like you whizzing a ball round on a string. And as a result, the moon is getting faster and faster, and this is enabling it to get further and further away from Earth. So it's getting about 3 centimetres further from Earth every single year. So the Earth isn't in perpetual motion because it's giving away some of its energy to the moon. And if you wait about 600 million years, then you won't have a moon anymore, because we won't have tides, because the moon will have gone.
Thank you very much.
Tony, thank you very much. My mind is boggled now, but thank you very much. Take care. So, Chris, a question from Derek on the road. A friend of his who's 65 has been diagnosed with diabetes. What is diabetes and what causes it, and can we do anything to avoid it? Is it hereditary? Chris?
Well, diabetes got named by Thomas Willis, who was an English anatomist, and he called diabetes because diabetes is a Greek word for siphon. And Thomas Willis famously said, people with diabetes piss a plenty. In other words, they go to the wee a lot. And the reason for that is because diabetes is usually, in the type that we're talking about here, diabetes mellitus. Mm-hmm. It's too much sugar in the bloodstream. And when you have high blood sugar, the kidney filters your blood, and the sugar which is dissolved in the blood gets filtered out by the kidney and then passes into the urine. And because the sugar attracts water to itself, it holds on to a lot more water in the urine than you should have in your urine, which is why you go to the loo a lot. Why do you have this high blood sugar? The reason is that your pancreas, which is an organ in your abdomen which sits just beneath your liver and in the crook of a loop of your small bowel called the duodenum, the pancreas contains cells called beta islets of Langerhans. And these beta cells have chemical docking stations on their surfaces for glucose, the molecule of sugar, mm-hmm. and they constantly taste the blood to see how much sugar is present. And when the blood sugar level rises, these cells detect that, and they then produce the protein hormone insulin, which is a short sequence. It's about 54 amino acids, which comes out of those cells, goes around in the bloodstream, and cells that then are in contact with the blood see that hormone signal, and it docks with a chemical docking station on the surfaces of those cells and tells them the blood sugar is too high, you need to take some glucose inside your cells and then lock it away chemically as other things or metabolize it. And so the cells hear that signal and they start turning on transporters, which are like little vacuum cleaners for sugar, and they remove the blood sugar from the bloodstream, which reduces blood sugar. Now, in some people, they don't have enough insulin in the body, and there's 2 reasons why that can happen. One is that, and usually in very young people, in their early teen years, they get type 1 diabetes. This is where the immune system, for reasons we don't fully understand, but it might be provoked by an infection or a virus, but could also have a genetic basis. This is where the immune system, for some reason, attacks those beta cells in the pancreas and kills them. And as a result, the people cannot make any insulin. And because they can't make any insulin, the cells around the body which would normally respond to that insulin signal to get the blood sugar out of the blood and put it into the cells, that signal's not there. So the cells leave the blood, the glucose in the bloodstream, and blood sugar gets very, very high, and the cells themselves are effectively starving. They can't get enough glucose in. That's type 1 diabetes. The other type of diabetes is called type 2 diabetes, and this is also known as maturity onset diabetes, and it's associated with being overweight. We don't exactly understand why, but people are beginning to get some insights now. But when you gain too much weight, your body becomes resistant to your own insulin. You need much more insulin than normal to maintain a healthy blood sugar level. And scientists are beginning to understand a bit more about why that happens, but this condition of insulin insensitivity is probably what leads to people ending up with very high blood sugar levels when they have too much weight on board. And because the pancreas is having to work so hard to produce this extra insulin it needs, eventually it burns out and can't cope. And then you end up with too little insulin and you become diabetic. The consequence of having this very high blood sugar is that the glucose, which is going around in the bloodstream, can lock on to other things that it shouldn't do normally. And it forms something called an advanced glycation end product. And you get glucose stuck onto various membranes and can make them thicker. It can also affect the ability of your immune system to fight off disease. And it also adversely affects the levels of fats in the bloodstream. And this can clog up arteries. So people who have diabetes have to be very careful to maintain a healthy diet because you can get blocked up blood vessels, and this can lead to tissues becoming insufficiently supplied with blood, and you can get gangrene. The other organs that can be affected in the same way include your kidneys and also your eyes, because the poor blood vessels that you get with diabetes can mean that you don't get enough oxygen going to some of the tissues, and as a result the tissues in the retina, for example, which are very oxygen sensitive, start to produce signals saying, make more blood vessels because I'm not getting enough oxygen. But the blood vessels that form are quite weak and they're quite leaky. And as a result, you don't then end up with the blood staying in the blood vessels. It leaks out into the retina, where the iron in the haemoglobin is poisonous to the retina, and it can cause blindness. And that's why doctors use lasers to damage those and destroy those new blood vessels, which are weak, to stop them leaking. So the bottom line with diabetes is that it's bad news. It costs the NHS about £1.75 billion a year to treat it. And because of that, we're eagerly looking for ways to prevent people getting diabetes and also prevent them from getting the complications of diabetes. And it can be dealt with, as long as you're careful, with taking insulin, or if you've got type 2 diabetes, tablets. And these can enable you to control blood sugar very carefully, because if you can do that, then you can minimise the risk of getting these side effects. But it does take a lot of care, and so people who have diabetes can control their condition, but they just need to be very careful to watch what they eat, watch their blood sugar levels, keep their blood sugar under control, and that's compatible then with the best possible outcomes.
Is it a hereditary condition?
Well, type 2 diabetes does seem to have a number of genes associated with it, and scientists have now been using a technique called SNPs, single nucleotide polymorphism analysis. And what this involves is you take a group of people who have a condition, you take another group of people who don't have a condition, and you screen their genomes for these molecular tags called SNPs to see if the people who have the condition have hotspots in their genomes compared with the people who don't have the condition, who don't seem to have that hotspot, these clustering of these chemical flags. And then what you do is you home in on the areas which are flagged up as more commonly occurring in the people with the condition, and you see if there are genes in that area which might be linked to the disease. And they've begun to uncover a number of possible gene associations with diabetes. So the answer is yes, there is a genetic element to this, but there's also an environmental element, and that means in the case of type 2 diabetes, eating too much, and in the case of type 1 diabetes, it's probably maybe some viral infection which comes into contact with certain people's immune systems, and there's a sort of killer combo, a certain immune configuration and a certain viral infection which seems to trigger it off. But to be honest, we don't yet have a test which says, I can test you for this and you're going to get diabetes. That doesn't exist yet, heaven forbid, because when it does, I think insurance companies will start asking us for blood samples.
Mm-hmm. Dr. Chris, thank you for that one. I've learnt loads there. If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. We've got Bob on the line from Dunstable. Good evening, Bob.
Hello, Sue. Hello, Chris.
Hi, Bob.
What's your question, Bob?
Right, I'm a bit of a gadget fanatic, and the latest gadget that I've got has got people saying, how the hell does it work? And I can't answer that. All I'd put it down to is chemical reaction. What it is like a plastic pouch with a liquid inside, and it's got a metal tag that you click, and you click it, and it all turns white, and it heats up. Where does it get the heat from? How does it work? How does it do it? And then when it's cooled down, you boil it up again, and you can use it again a second time. You keep on using it. It's been great over the cold weather, but I just don't know how it works.
I had one of those when I was little and I loved it. They're absolutely fantastic, aren't they? And the chemical that's inside there is the same stuff that makes salt and vinegar crisps taste nice. It's called sodium acetate, which is acetic acid, which is what you find in vinegar, reacted with sodium. And it's actually a very safe chemical, but what it does do when you make a super saturated solution, so in other words, you take some water and you dissolve as much of that chemical in it as you possibly can, what it then does is very readily start to form crystals. And that little disc, if you look in your pouch, the disc inside it is irregularly surfaced. It's got a rough contour. You'll see there's little spikes or jagged raised leaves of metal on it.
Right.
And it's also curved, a bit like a crescent moon.
That's right, yeah.
And you can pop it from one configuration to the other.
Yeah.
It's a bit like having half a tennis ball and you can turn it inside out and make it flick back and forth.
Yeah, like a little
And
clicker,
when you flick that disc back and forth, what it does is it exposes some of these jagged surfaces, and this gives what are called nucleation sites to the sodium acetate. So in other words, the rough surface gives a key or a mounting point for the crystal to begin to form. And then, once you've started crystals forming, it's much easier for other crystals to start to lock on. And before long, you start to form these giant crystal lattices which fill the entire packet because it's supersaturated and it wants to form lots of crystals. Now, why should it go from being a liquid to being a solid? Well, in nature, things want to become more disorganised. That's called entropy. If you look at the universe, entropy is always increasing. Everything's going from a state of organisation to disorganisation. So why does this want to form a solid? Because that's highly organised. The answer is that by giving out huge amounts of heat energy, it's effectively dispersing things into the environment. It's giving energy to the environment, which is payback for the fact that it's becoming more organised as a crystal locally. So the entropy of the universe increases, but the organisation of your little heat pack becomes more organised, but that's a small price to pay for that huge release of energy. And the reason it's reversible is that when you put the energy back in by boiling it in some hot water, then the water that's in there can redissolve the crystals. They all spread out again, and the whole thing is reset. And then you get the energy back out when it recrystallises, because when things form crystals, they release what's called latent heat of crystallisation, and that's what you're seeing. It's what warms your hands up.
That's great. I just wondered where they got the heat from.
Well, the heat comes from the fact that you've boiled it in a pan of hot water. So you put the energy in, and it stores it for you, and then you get it back.
That's great.
All right, Bob. OK, thank you.
Bye-bye.
Thanks very much, Bob from Dunstable. Now, some more questions. Richard and Marianne, Dr. Chris, they say, why does their DAB radio work perfectly outside, but when they bring it inside, it picks up nothing? They live on a narrowboat. Will it affect it?
Possibly. The thing about digital radio is that you either hear perfect signal or you hear nothing. And the reason for that is that digital radio is a system of noughts and ones. So in the radio station, the sounds of microphones and the energy from the desk and the mix of people talking into microphones is converted not into a wiggly wave, an analogue wave, but it's converted into a series of noughts and ones, on or off. And those are what get transmitted. The digital radio picks up those noughts and ones, and then it decodes them because it knows what the code is that's been used to write them, and it rebuilds or recreates the wiggly wave that are the sound waves that you can hear. But it can only do that if there is faithful presentation of that series of digital noughts and ones to the radio. If the signal gets interrupted, then it loses count of how to rebuild the wave, and it stops. So in other words, if you're at the very vestiges, the very edge of a broadcast area, and you can just about have enough signal, with digital, you'll still get perfect signal. You'll still get a perfect representation of the sound that the person was producing in their studio. But if you then move the radio a little bit so the signal is just off the edge of what can now be used, it completely goes off. And when they put when Richard and Marianne put their radio on their boat, there are two possibilities. One is that the boat could have a lot of metal in the canopy, and the metal is screening out the radio waves. The second is that boats are usually below the level of the surrounding land because water obviously sinks to the lowest level. Rivers are usually recessed a little bit, and as a result they may be now just off the edge of where the radio signal can see their aerial, and as a result they don't get anything.
OK. Dr. Chris, we have a question here from Steve in Bury St Edmunds and also a caller on the line. Steve asks, who made the first perfectly straight object? Whoever they were, what did they use to do this?
Yes, well, the answer to how you make a straight thing is, well, there's two ways of doing this. One is that you can use the fact that if you take a stick it in the ground and you tie a bit of string on it, and then you pull the string outwards, you can then do two things. One, if you just stick another stick in the ground, you have a straight line between the two of them, which is your piece of string. The second thing is, if you walk around and try and walk in a straight line, holding the end of the string, of course you'll be pulled in towards the stick and you'll go around in a circle. So that was actually how people did it in the early days. That was how they got straight lines and also made circles. And they were doing that, well, we know the wheel goes back about 5,000 years. So they were obviously up to those kind of tricks at least 5,000 years ago, and certainly probably longer than that, I would think.
Thank you, Chris. Now then, on the phone we have Tony. Hello, Tony.
Bonsoir, madame.
Bonsoir. Your question for Chris.
Right. It's really, I was rather interested how we have a body heat of 98.4 in old language. How does the body manage to maintain that heat?
The answer is, Tony, that, not to put too fine a point on it, you're a giant bag of chemical reactions. And you have a number of organ systems in your body that are very metabolically active. Your muscles are one of them, your liver's another, and also your digestive system is full of bacteria. There are something like 50 times as many bacterial cells in your body as there are human cells, and they're all producing chemical reactions which all release heat. And so as a result of just living, you are producing heat. And although we talk about certain animals like fish as being cold-blooded, in fact, if you make measurements from the interior of things like salmon sharks, very big fish, you find that they are hot. And they're almost the same temperature as us inside. In fact, the dinosaurs were so big that their core body temperature was probably on par with ours and probably a constant hot temperature because they just couldn't lose the heat fast enough. What we've done is to adapt ourselves to make sure we maintain a very tightly regulated body temperature so we can tweak the speed of those chemical reactions. We use things like thyroxine, our body's thermostatic chemical, to do that. And we also have other mechanisms such as behaviour. You put on a jumper, you also pylo-erect, you make your hair stand on end, and you clamp down blood flow to your skin to conserve heat. You can do the reverse to lose heat on hot days. So we have these various mechanisms that keep the heat in. We have chemical reactions to make it for us in the first place.
Having heard that, if I put a few jumpers on, for example, and it's cold, does that affect makes my feet seem to get cold? Does the heat go to the whole body, or if I make the top part hot, as it were, would the bottom part not get so much heat in it? In a nutshell, my feet are cold, my top's hot.
Yeah, well, there are two things going on. One is central control and one is local control. What I mean by that is your body's priority is to try to conserve your core body temperature, and that means the middle of your body and your nervous system, and that gets priority over everything else because those are the most sensitive tissues. So the body achieves that in two ways. One is that when the core temperature is threatened, then it says, right, okay, I want to withdraw blood flow to all of the non-essential tissues. And the first non-essential tissue to go are your peripheries, skin and distal extremities, fingers and toes. So the blood vessels supplying those areas are vasoconstricted. They're tightened down, therefore reducing the amount of blood that can flow through them, therefore reducing how much heat can be lost from that bit of the body. At the same time, there's also something called local control, in the same way that if you stick your hand in the freezer, the local tissues in your hand detect the fact that your hand is very, very cold and that you're hemorrhaging heat through that part of your body. And so there's an intense local vasoconstriction to minimise heat loss from that part of the body. And as a result, when you put your jumpers on, the top half of your body can be warm because it's saying, well, I've got plenty of heat up here, but there can still be local effects. If you don't put your slippers on, your feet can still detect that it's cold and they will constrict a little bit to minimise heat loss through that area. The time when this doesn't happen is if you are very, very, very hot and the body has to lose heat somehow, and then special mechanisms of vasodilatation can kick in. This is where the nervous system tells blood vessels to open up, thereby acting like radiators to get heat out of the body. But you'd have to get really quite hot for that to happen, so I suspect with your 2 jumpers on, it's not going to happen. The best way actually to get warm is to do a little bit of exercise. Just walking around is very good because it gets muscles going. Muscles make heat, and at the same time you've got to open up blood vessels to supply those muscles, so it gets more heat into the distal extremities, and so it sort of kills 2 birds with 1 stone.
Barbara has sent a question in asking what causes the dehydration related to diabetes.
Well, the reason for that is that because you have higher than normal levels of blood sugar, glucose, going round, when this goes through the kidney normally scavenges back glucose from the urine because it has a glucose transporter which can pick up any glucose that the body has lost in urine and put it back into the bloodstream. But because there is only so many of those transporters, as the level of glucose in the blood rises, eventually it overwhelms the ability of the kidney to suck the glucose back into the bloodstream. You can bring back in about 10 millimolar of glucose. Any level beyond that and you lose it. And because glucose is osmotically active, in other words, it's a salt or a sugar which, when dissolved in water, pulls water into itself, it attracts water. This means that this adds to the ability of the water in the kidney tubule to pull water out of your tissues. So it's a bit like putting salt on a slug, only in this case, what you've got is the sugar inside the urine, and it's pulling water out of your body and hanging onto it and making you make more urine than you should. And therefore it has a dehydrating effect. So people who don't have enough insulin, this is usually people who have type 1 diabetes. They can have something called a diabetic ketoacidosis, and this is where they can get very high levels of blood sugar, and this will dehydrate them, and as a result they can need very, very large amounts of liquid very, very quickly, and that's usually done in a hospital setting because it's a medical emergency. But thankfully it doesn't happen too often because most people know to take their insulin on time regularly and not let themselves get like that.
And lastly, from Paul, he asked by email, why is there a periodic table, like all the chemical symbols and the order that they're in? Why is that?
Well, the periodic table was actually the work of a scientist called Dmitry Mendeleev. He was a Russian scientist, and the reason that we have a periodic table, and it's called periodic, is because what scientists began to realise is that there are lots of elements on Earth, the elements are the building blocks of the world around us, but if you follow these elements and look at them, you'll see that they periodically show very similar behaviours. And that's because they are chemically very similar, some of them, to each other. So if you look at the chemicals like chlorine and fluorine and bromine and iodine, they're all the halogens. They're in group 7 of the periodic table. They all show related behaviours. They all react in very similar ways. They just differ in the size of their atoms. The metals are the same. There's group 1 metals like lithium at the top, and then there's sodium and potassium and so on and so forth. And so the periodic table is a very useful way of arranging all of the chemicals that we see on Earth around us into their respective groups so that we know how any given chemical will behave and also how big it is and therefore what its weight is, because then we know how much of it we're dealing with. So it's a very useful predictor of behaviour and also a very useful way for scientists to work out what to mix with what in what proportions.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.